What if high blood pressure isn't really a pressure problem? What if it's a flow problem? For decades, attention in cardiovascular disease has focused on large arteries, blocked, narrowed, hardened. But what if the real bottleneck exists somewhere else entirely? Somewhere microscopic. Because the true purpose of circulation is not pressure, it's delivery. The body does not care how much blood is moving through the major arteries if oxygen and nutrients cannot actually reach the tissues. That final delivery happens inside the microcirculation. Tiny capillaries so small that red blood cells pass through them in a single file. So this is where oxygen leaves the blood, where nutrients enter the cells, where life itself is exchanged moment by moment. But under chronic stress and inflammation, these microscopic pathways begin slowly closing, not through dramatic clots, but through subtle changes in flow, fibrin accumulation, and vascular constriction. The heart responds by pushing harder. The heart pumps harder while the cells quietly starve. And this may fundamentally change how we understand hypertension, fatigue, brain fog, and chronic disease itself. When most people think about circulation, they picture the heart, large arteries, large veins, but those large vessels are only part of the story. The true work of circulation happens inside the microcirculation, a vast hidden network of arteries, venules, and capillaries. So small, so numerous, so critical. This is where oxygen actually leaves the bloodstream, where nutrients enter tissues, where waste is removed. Without the microcirculation, the larger vessels become meaningless highways, leading nowhere. Imagine a massive city with enormous freeways, but every neighborhood street is blocked. Cars still move on highways, but nothing important can actually be delivered. This is what happens when the microcirculation begins failing. Because the microcirculation contains the overwhelming majority of blood vessels in the body, small dysfunctions spread across the network can create massive systemic consequences. Fatigue, brain fog, cold hands and feet, hypertension, inflammation, not because blood is absent, but because delivery itself is becoming impaired. The microcirculation is also extremely sensitive to stress, especially chronic stress. When the body enters prolonged sympathetic activation, the smallest vessels often begin changing first. Not dramatically, not all at once, but slowly, subtly, microscopically. Flow becomes less smooth, vessels become less flexible, oxygen becomes less efficient. Which brings us to the most important, fascinating ideas of vascular physiology. What determines whether these tiny vessels remain open or begin closing? Dr. Lewis Coleman, in his work on chronic disease and microvascular dysfunction, proposed that many conditions may originate not in the large arteries, but deep within the capillary network itself. At the center of this process is the endothelium, the thin, intelligent lining inside every blood vessel. It constantly monitors stress hormones, oxygen levels, inflammatory signals, and clotting activity. Under healthy conditions, the capillary network remains flexible, open, responsive. Blood vessels move smoothly, oxygen unloads efficiently, cells remain nourished, but under chronic stress, the environment shifts. Stress hormones rise, inflammation increases, the clotting system activates, and slowly, tiny fibrin strands begin accumulating inside the microcirculation. Fibrin is a sticky protein used to stabilize blood clots. In an actual injury, this is protective, life-saving. But fibrin accumulates chronically inside microscopic vessels. It creates resistance. Tiny interior barriers, tiny choke points inside the capillary network, almost like microscopic spider webs forming throughout the circulation. Flow becomes sluggish, oxygen delivery becomes less reliable. Certain capillary pathways begin functionally closing. And the body responds the only way it knows how. It increases pressure. This is the hydraulic paradox. Imagine trying to force water through a clogged garden hose. Pressure builds behind the obstruction, but despite increased force, flow at the far end remains compromised. The heart contracts more forcefully, vascular tension rises, but the underlying obstruction still exists. And because the bottleneck occurs deep inside the small vessels, high blood pressure alone often cannot restore delivery. This is why a person can simultaneously have elevated blood pressure, poor circulation, fatigue, cold extremities, and brain fog all at the same time. The body is generating enormous force while delivery remains impaired. Over time, this increased pressure begins damaging the vascular system itself. Vessel walls stiffen, the endothelium becomes inflamed, and eventually the body may begin eliminating portions of the microvascular network entirely. This process is called capillary refraction. The delivery network itself begins shrinking, which creates even more resistance, even more pressure, a vicious cycle. Elevated blood pressure may not always represent a primary pressure disorder. It may represent the body's desperate attempt to overcome resistance inside an increasingly obstructed terrain. For many years, the idea that microscopic clotting could drive widespread chronic symptoms was largely overlooked. Then came the investigation into long COVID. Many patients experienced severe fatigue, brain fog, shortness of breath, and profound exercise intolerance. Standard testing often appeared relatively normal. Major arteries looked open, blood oxygen saturation could appear acceptable. Yet patients felt profoundly unwell, almost as though oxygen was failing to properly reach the tissues. Then researchers discovered something remarkable. Persistent microclots, tiny fibrin-based obstructions circulating throughout the bloodstream. Not massive clots, but microscopic ones capable of interfering with normal microvascular flow and unusually resistant to breakdown. So this discovery was important for several reasons. It demonstrated that microscopic vascular obstruction can create profound systemic symptoms, even without major artery blockages. It confirmed that oxygen delivery problems can exist at the tissue level, even when blood oxygen levels appear normal. And it brought a new urgency to the hidden world of the microcirculation. Because the obstruction does not need to be massive to disrupt the terrain of the body. Tiny restrictions spread across millions of capillaries can create enormous physiological consequences. And while long COVID brought this into focus, the broader implications extend far beyond a single condition. Chronic stress, inflammation, prolonged sympathetic activation, these may all contribute to similar patterns of microvascular stagnation in people who have never even had long COVID at all. At this point, a deeper picture emerges. The body is not simply suffering from random dysfunction. It may be trapped inside a prolonged state of defense. The circulation tightens, the microvascular becomes resistant, fibrin accumulates, and the body responds with more pressure, more stress, chemistry, more vigilance. But force alone cannot restore healthy circulation. The body heals through regulation, through signaling, through chemistry. And it requires signals of safety, signals capable of telling the nervous system, the endothelium, the blood vessels, and the clotting system that the threat has passed. Until that signal arrives, the body may continue protecting itself indefinitely. There is one molecule deeply connected to relaxation, vascular openness, oxygen delivery, and parasympathetic regulation. A molecule that modern physiology has largely misunderstood, carbon dioxide. Most people think of carbon dioxide as simply a waste gas, something to exhale, something to eliminate. But carbon dioxide is also one of the body's most important biochemical regulators. It helps govern vessel tone, oxygen delivery, nervous system balance, and even clotting behavior itself. When carbon dioxide levels remain stable, blood vessels relax, microcirculation opens, oxygen unloads more efficiently into the tissues, the nervous system shifts towards parasympathetic dominance. The body receives chemistry consistent with safety. True recovery may not simply involve suppressing symptoms or forcing pressure lower. It may involve restoring the conditions under which the body finally feels safe enough to open circulation naturally. Safe enough to soften vascular tension, safe enough to restore flow, safe enough to release the defensive posture it has been holding for years. So in the next video, we'll explore exactly how carbon dioxide functions as a biochemical signal of safety and what it means for blood vessels, oxygen delivery, the nervous system, and the restoration of microvascular flow. Because healing may begin when the body finally receives the chemistry of safety.